In this lecture, we're going to cover layer 3 of the OSI model, which is the network layer. The network layer is responsible for routing packets to their destination on the network. So this is why routers operate at the network layer. And it's also responsible for quality of service as well. What quality of service is, you might have one particular type of traffic that requires a better level of service than another level of traffic. For example, if you're running voice or video over IP, it's sensitive to delay, so we're going to give it better quality service than something like email. IP, Internet Protocol, is the best known layer 3 protocol. IPv4 is the focus of this section. There's also IPv6 as well, which is the upgrade for IPv4. Later on throughout the course, we'll be talking about why we have IPv6 and also its actual usage today and how to configure it. IP is a connectionless protocol, so there's no acknowledgements at layer 3. You can still have reliable traffic by using TCP and its acknowledgements at layer 4 or by having it built into the upper layers. Other layer 3 protocols apart from IP include ICMP, which is the Internet Control Message Protocol, which is used for ping for troubleshooting, which we'll also be talking about later in the course, and also IPsec for secure encrypted communications. There are other protocols as well, but IP is the best known one, by far the most commonly used. That's what we're going to be talking about in this entire section. IP addressing is a logical addressing scheme which is implemented at layer 3. So the network designer uses IP addressing to partition the overall network into smaller subnetworks, or commonly called subnets. By having different subnets, it improves performance and security and makes troubleshooting easier. It improves performance because rather than having one big flat network, we divide it into smaller subnets and we can keep the traffic on the particular subnet that it needs to be on rather than going everywhere. So we get better performance that way. We also get better security by having this logical addressing as well. For example, let's say that we've got accounting servers. We can put them on one particular subnet, and that makes it really easy to control who's got access to those servers. Also, it makes troubleshooting easier as well, because by partitioning the network into smaller parts, if we have a problem, it's easy to see what part of the network the problem is on and concentrate there. So that's our layer 3 addressing, uses IP addresses. At layer 2, which we'll get to soon in the next section, we have MAC addresses if we're using Ethernet. IP addresses layer 3, MAC addresses layer 2. IP address is a logical addressing scheme. MAC addresses is just one big flat global addressing scheme. So you'll see this section is going to be a lot longer, more involved than when we get to MAC addresses, because there's a lot more work to do here. There's no logical separation at layer 2 of the OSI model. It's done here at layer 3 with our IP addressing. Okay, this is the first lecture in our layer 3 section. So as usual, we'll have a review of the OSI stack again. You're going to see this several times because it's important, and I really want to drill into you about how networking works based on the OSI model. So again, we've got the 7 layers. Layer 7 is the application layer. When a sender is going to send traffic, it composes the packet. It creates the layer 7 information first. That then gets encapsulated in the layer 6 presentation layer header, then encapsulated in the session layer header. Top 3 layers are our upper layers, mostly the concern of application developers. As networkers, we start getting really interested at layer 4. So the packet, we've got layer 765, it then gets encapsulated with the layer 4 header, and that will either be a TCP or a UDP header, and the port information will be on there. That then gets further encapsulated in the layer 3 header, which is the subject of this section. Main information in the layer 3 header is the IP address information, but you'll see coming up shortly the rest of the information that's also in the header. Our network infrastructure device that works at layer 3 is our routers. Then we carry on making the packet. We put on the layer 2 header, which is the data link header, on a local area network that will be using Ethernet, and we'll have the source and destination MAC address there. Our network devices that work at layer 2 are our switches. Finally, the packet will actually get put onto the physical wire, that's at the physical layer, and our hubs work at the physical layer. Not that we still have hubs, we'll talk about that a bit more later too. Okay, last slide in this lecture, we're going to take a look at the IP header. So the top row that you see there, first part is a 4-bit version. It's either going to be IP version 4 or IP version 6. That's referenced in that field. We then have the 4-bit header length, the length of the IP header. It can be a different length because the header options that you see further down can be variable length. We then have the type of service byte. This is used for quality of service information. So we can put a marking on the packet to specify what kind of traffic this is. And on our routers later, we can take an action based on that marking to give it better service if we need to. For example, for our voice over IP traffic. We then have the 16-bit total length of the packet. The next row underneath is used for fragment information. With our different media types, for example, Ethernet, there is a maximum transmission unit size, the maximum size of the packet. Maximum size by default in Ethernet is a 1500 byte MTU. If we try to put a packet onto the wire that is larger than that size, it has to get split up into smaller parts, which are called our fragments. The second row of information on the IP header is used to help keep track of those fragments. The next row down, we have an 8-bit time to live field. Every time a packet goes through a router, the router will decrement the TTL field by 1. If it gets down to 0, then that router will drop the packet. What this is for is to prevent routing loops. We might have an error in our network somewhere that is causing packets to endlessly loop around the network without ever getting to their destination. We don't want packets to loop around forever, so TTL will prevent that and drop them. Now, it doesn't fix the underlying problem. We still need to cure the loop so that traffic will actually get there, but it stops us from having a huge amount of traffic getting built up on our network, slowing it down, which is just looping. The next field, the 8-bit protocol, that will specify the layer 4 information type, typically TCP or UDP. We then have a checksum, which is used to check that the packet has not been corrupted in transit. Next, we have the source IP address, specifying where the packet came from, and then the destination IP address, specifying where the packet is going to. The next field is the header options, where we can put in additional information. It's not commonly used. And finally, we have the data, the rest of the packet. Thanks for watching. If you want to get hands-on practice with Cisco networks for free, then you can download my 400-page CCNA Lab Guide, which you can see above my head right now. Also, check out the video about my CCNA course. It's the highest rated course online. Thanks.